You good, Josh? Luke. All right. You ready? Yeah. That's the spirit. Okay. I was reviewing the chapters and notes and looking what holes I left out. So let's see. There were two things. I'm going to start with an animation here. So, buoyant force. We got two ways to look at whether things sink or float. Just resolution of forces. If the weight is greater than the buoyant force, it goes down. If the buoyant force is greater than the weight, it rises up. And if they're equal, it stays put. What happens when something comes up to the top and it's floating on the surface, like a ship? How do the two forces compare then? It's floating, so we got to vote for equal. What'd you say? We got one vote for the buoyant force is greater. Somebody break the tie. It's floating on the top of the surface. So it's partially submerged. It's immersed. So we need one more vote to break the tie. Say buoyant force is greater. Okay. So the buoyant forces are greater, we'll have it. If this is bigger, what's the net force? In what direction? Up. Does a ship keep moving up? At some point, it stops moving up. Nor is it moving down. Do you want to change your answer? So once it rises to the top and stays put, they're equal. How can they be equal, though, if it's floating? Because I thought we said this one's bigger when it's floating. I mean, if this is bigger, it rises up. But at some point, it comes out of the water partially. And now they're equal. So what's going on?
A floating object displaces its own weight, or the amount of water that weighs its own weight equals its own weight. There we go.
It displaces its own weight of water?
Yeah.
So how much water is like a ship displacing when it's on the surface?
The same as its own weight.
The same as its own weight. What if you submerge the ship? Well, it depends on if it's going to sink or not. I guess my point here is once it comes to the surface, it's not completely submerged, so it's no longer displacing its entire volume. Think of a submarine. Might be easier because it's enclosed. If a submarine's underwater, it displaces its entire volume of water, right? And that creates the buoyant force. So if that buoyant force is enough, more than its weight, then it rises to the surface. But when it comes to the surface, it's no longer displacing its entire volume. Just enough to keep it on the surface. So if it's underneath, it displaces its whole volume, and that's a big enough buoyant force to raise it up. But as it comes out of the water, it doesn't displace as much, so the buoyant force on it goes down until it's just balanced. So my point here, anything you see floating on top of water, you know something automatically now. The buoyant force is its weight once it's on the top. So if you have a 20,000 Newton ship floating in the ocean, you automatically know what the buoyant force is. It must be 20,000 newtons because it's not going up and it's not going down. It's displacing just enough water to counter its weight. So remember the difference when it's on the surface and only partially under versus completely under. Now, the point of this is, what if you go farther under? How does the buoyant force change? Take that submarine. Forget that. Take a life preserver. Nah, that didn't work either. We'll stick with a submarine. Okay, When it's completely underwater, it displaces its whole volume of water, and there's a certain buoyant force on it. What happens when it goes to the bottom of the ocean? What happens to the buoyant force on it? It stays the same. Very good. Because it's not displacing any more volume or less. Remember, buoyant force is dependent on the volume of fluid displaced. It displaces the same amount whether it's up top, but still underneath, or really deep. So this is another way to look at buoyant force. Little animation the author made. I'll give him the credit. So here's the forces that the water pushes on it. If you go deeper underneath the water, see the forces increase, right? Pressure is depth dependent. Let's go as far as this will go. They get bigger. Something you might not realize, though, let's make it more obvious by increasing the height of the object. I'll raise it up slightly. So, do you see the forces down here pushing on the bottom of it? They're greater than the forces pushing up here. Why is that? Yeah, the bottom of an object's deeper. Notice the sides, same. These are greater than up here. But on the sides, these cancel each other out so it doesn't move sideways. But these do not. This is larger on the bottom than it is on the top. It's the difference in pressures from the bottom and the top that causes this buoyant force. And if that object is up top, let's raise it back up a little bit. There's still a difference between the pressure on the bottom and the pressure on the top, and that difference is the buoyant force. It's the same difference when it's down here. It's just the pressures are bigger in the first place, but the difference is the same. That's why a buoyant force wouldn't change on an object that's not changing its volume the deeper and deeper it goes. What's something that would change its volume the deeper and deeper it goes? You know this one. What could you take like to the bottom of the ocean? Basically, if it's not rigid. A balloon. Yeah, what would happen to a balloon as you took it deeper and deeper? That's right, it would get smaller. That would do what to its density? It would increase its density. And if its density becomes greater than the water, what happens? Yeah, you can let go of it and it will no longer raise to the top. It would sink. That happens to us too. We're not as rigid as we like to think. You can only go so far down in the ocean, and the pressure on you increases, and will actually do what to your density? Increase it. Yeah, the air in your lungs gets harder to breathe. That's why they pressurize air tanks. And at some point, your density will become larger than that of water because of this increased pressure. And if you just relax, you don't automatically float up. You actually can start sinking. That'd be a weird feeling, wouldn't it? So I thought that would help, that little animation. Now let's do several questions. See what you're getting. Clicker time. That's not it. I always do that and I don't mean to. All right, there's the session ID number. Polling's open, so once you get logged in, answer away. And we'll see if we have any remaining confusions. Anybody ever laid down on a bed of nails? I have one back here. I haven't brought it out yet. Doesn't hurt, does it? I wouldn't say it's comfortable, but yeah. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, 2/3 of you think B. You're right. This is just this guide to our thinking. To remind you pressure is what? Force over an area. There you go. So if you spread the same force over more area, more nails, there's less pressure. That was the Dixie cup demo I did, yeah. And if I had enough Dixie cups, they each held up less force individually, and they could handle that. But 4, nope, I'm too fat for that. Oh. All right, go. What does water pressure depend on? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, bless you. 80% of you C. That's correct. It's only depth dependent. Doesn't care how much water's above it, volume. Just how far down you are. You can be the same depth in the ocean or a swimming pool. If you're at the same depth, it'll be the same pressure. All right. Let's see if you can answer this one. Remember we had those vases that were different shapes? It was just depth dependent. You can picture that, like it's a tube full of a liquid. The pressure at the bottom is based on how much liquid's above it. But one's fresh water and one's salt water. How does that change things? Oh, you've all pretty much voted. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right. Most of you B. That's correct. As it says there, salt water is more dense. So not only does pressure depend on the depth, it depends on density. Density, gravity, and how much fluid's above you or how deep you are in it. So the density of salt water is more. You added salt to the water, so it has more density for the same, more mass for the same volume. So that will create more pressure down at the bottom. Any questions? All right, which one do I want to do next? This one. So given that, and what we talked about, hopefully we can get this one. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right. Good. We get to talk amongst yourselves. We'll ask it again. Most of you think A or B there. Decreases or remains unchanged. Oh, explain yourselves to your neighbors and see if we can resolve some of this. If you've come to a consensus, you can go ahead and vote again. If you're still confused, we asked about buoyant force. What else is happening? That's probably why most people get confused with it. Other things are happening, but I asked about the buoyant force. So maybe if you can look at everything that's going on, that might help you. You can, if you choose A and then you decide to choose B, just hit B. It'll replace it. Yeah. And I'm witnessing this. I hope you guys realize, I can tell that when you guys actually try to verbalize and discuss, you're learning better. You're going to remember this one more. I can tell. Well, I'm going to make you decide, I guess. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. There they are. Okay, we shifted more to B. Well, you're right. All right, somebody that got it right, would you like to brave an explanation? Because you're feeling good that you were right, so I'll ask you guys. Any takers? All right, thanks.
All right, so my thinking was that the 20,000 meter ship was floating in both saltwater and freshwater.
It's floating in both, correct.
So then the buoyant force is going to be at least equal to 20,000.
Then the buoyant force is exactly equal to 20,000. Remember, if it's floating on the... It's exactly balancing its weight. So the buoyant force doesn't change. Because it's floating on the surface. What will be different? The density of water is different. Salt water is more dense. So what will that do to the ship? Yeah, it changes that difference in pressure. That's not true. There's pressure differences, but not for buoyant force.
So I had a question regarding that. So I was looking at that formula and I thought the density increases and then the pressure increases as well. And then pressure is proportional to force, but maybe that doesn't apply to buoyant force.
These are happening. Before I explain these more, what's physically happening to the ship? What do you think? There you go. Which way are we going? So I say it right. Passes from salt water to fresh water. Okay, so it's going from the more dense to the less dense. Is the density of the ship changing? No. Okay, so if we're in less dense water, it'll probably start out so far underwater. Well, sunk in. If you go to something that's now, I said that the wrong way, didn't I? It's in more dense. Salt water is more dense. Sorry. So if it's more dense, basically, is the ship's going to move? Is it going to rise up a little or sink a little?
Saltwater should rise up a little.
Your answer's on the bottom all along. It floats a little bit lower, so you're right. Because fresh water is not as dense. It does not create as big a pressure to hold it up. But look at it this way. If it sinks a little lower, it displaces more water, doesn't it? A little bit lower in the fresh water. Why does it need to displace more water? Because the water it's displacing now isn't as dense. In order to support the weight of the ship, it needs an equal buoyant force. In order to create that same buoyant force in fresh water that's less dense, it must displace more of it, so it sinks a little lower.
So you're saying even though the volume, since it's a bigger volume in the fresh water that's underwater, right?
Correct. There's a bigger volume under fresh water for the
Water's
water.
less dense, so it has to have more water, so that's why it
Exactly.
stays the same.
Yes.
Okay, that makes sense.
Yeah. For the camera, that's what I just said. So yes, very good. Any confusions on this at this point? So if it's floating on the top and it's 20,000 newton ship, then the buoyant force is 20,000 newtons. The buoyant force does not change. But if you change the fluid being displaced to create that buoyant force, you might have to displace more or less of it because it's of its density. And ships really have to worry about this when they're switching, especially if they're really weighted down. Because if they're like to the limit and they move into fresh water, they could capsize and sink because they're going to sink a little lower. Oh, helps if I show it. There we go. I have not discussed this. This is more have to tell me too. How many of you are actually reading the book? This was featured a lot in the chapter, so. Since the responses are slower, I can already tell. Let's just see what you're thinking. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. That means no idea. That's how I interpret that. I'm just going to give you the answer for a teaching moment in that case. And encourage you at this point to read the text. If you don't feel like you're doing as well or as confident about this stuff as you'd like just coming to class, well, that's what this is for, to help you. Friendly reminder, there's checkpoint questions that are like this that you can think about on your own, and then he gives explanations after you've thought about it. You know, there's questions at the end of the chapter. Lots of practice. Say maybe you do well in class or on the homework, but you seem to bomb the test. You want more practice? All the odd answers are in the back. The TA is telling me hardly anybody comes to see her. There's resources for you. I'm just reminding you of them. So this one is they used to have locks to move ships, and they'd have to raise and lower them to get one ship from somewhere to where else they wanted to go. But they weren't connected. It's kind of like a canal. Well, this Kirk Wheel replaced it. Basically, there's two sides. It spins around like this. They're kind of like buckets, like a Ferris wheel, if you know what I mean. And they keep them both full of water. And this one, the ship just kind of comes into this bucket, and it raises up, takes them up here, and they go away, or down, you know. But the biggest problem was like, but as soon as the ship comes in, it's going to be too heavy on that side, and it's not balanced, and it'll take too much energy to turn the thing. Well, this thing stays balanced the whole time, and it's a cool little principle of what you just learned. So let's go through it. If they're both full to the brim, they're both completely full of water, and a ship comes in, what's it going to do to the water in that bucket? Displace some of it. How much? Its own weight. And remember our top pan scales? When I put a ball in or I pushed on it, the buoyant force is there, and so the scale reacts to its weight. But we just displaced that much weight of water. So the weight stays the same. If it's completely full of water, it weighs so much. When a ship comes in and displaces its amount of water, it's still exactly the same weight. We added the weight of the ship, but we removed the weight of the water, which is exactly the same weight as the ship. Are you with me? It's ingenious, as long as they're to the brim, so the water can overflow. So you can reread some of that in the chapter if you want more about that.
Watch footage of it on YouTube. It's pretty cool.
Oh, I never even thought to get a video.
Just having a hard time envisioning it, so just YouTube. It's really cool.
Well, in this age, what the hey? Let's see if we can find it quickly enough. Kirk Wheel. How about this one? It looks shorter. Hopefully it's not just pictures. Okay, so you can see the ship going in. So the reservoir up top, up here, you can see this bucket, and he's going into the bucket down here. They're both full of water to the brim. So this one just displaced some water. Yeah, that's what I just told you. Blah, blah, blah. Pause that. So when it's halfway, you can see it's full of water here, it's full of water there. It just rotates easy. Since it's perfectly balanced, it takes, remarkably little amount of energy to rotate, even though that thing's tons. Just to if you ever balanced something and tried to rotate it, it's a piece of cake. As long as it's perfectly balanced. Look at there, the ship's on the left. And that saved hordes of money and time than going through a channel of locks that would then let water in and then water out. You'd have to do it multiple times. Ingenious. Physics! Well, as long as they fit in the bucket, that's the only. It's probably, yeah. All right, that's good. Let's call that good. Only because I can only handle the lights off so long. So, at the very end, we did the hovercraft of last lecture, and that is one more principle that I want to emphasize a little more since I whipped through it at the end there. And it's nothing new. It's this idea, named after Pascal. But it says in the book, a change in pressure at any point in an enclosed fluid. So you got this fluid, like water, and it's in a container. If you cause a change in pressure, like by increasing the pressure over on this end or pushing on it on this end, then wonderfully, that's transmitted to every other point equally in the fluid. So, practically, what does that mean? Something like this. If this is full of fluid, water, and you push on one side, that's going to be equally transmitted over to this side and vice versa. And that's how we're able to have hydraulics. Our brakes in our car. When you go fix your car and they raise your car up, or if you go watch next to the stadium, they got those big cranes to lift those things. In the back, they're using some hydraulics, or they can. Some do, some don't. Well, what's going on? This holds true on both sides. In this case, the pressure is the same. It's transmitted undiminished to all points. So the pressure in here is the same. You with me? It's enclosed. It's all together. So over here, see, pressure is going to be force over area. Well, this area is bigger, isn't it? Wow. And this area is small. So how are the forces going to compare? Exactly. A bigger force on the left. So that can mean with two things. You have to exert a whole lot of force here to have an effect over here. Or, the more practical, doesn't take much force here. Maybe I could do it, and I could lift a car up over here, depending on the ratio of the areas. Remember our simple machines? What does a simple machine, what can it never multiply? Very good. Energy. What can it multiply? Force, yeah. You can get more force out of one side than the other. Not at the expense of energy. That's always conserved. Total energy. But another thing happens too. If you get a whole lot more force out of this side than this side, which one's going to move further? If there's a change in energy and each gets the same energy, they each do the same amount of work. The work I do here is the same work that I get out here. I can't create more. So for a puny force, I'm going to have to move it a big distance to have the same work. So this side will have to move a lot further than this side. So I might not be able to lift the car very far, but I can do it now because the force is multiplied. Does that make sense? Just like with those simple machines? And that's hydraulics. And it works because of Pascal's principle. This formula, it works through an enclosed fluid. That pressure is transmitted equally everywhere. It's great. That's all there is to that. Questions? Okay then. Now everything we've discussed with water and liquids applies to gases. So the whole first half of chapter 15 we've just done. I'll go over it a little more, but because air is a fluid like liquid. So instead of thinking of a pool of water, think of a pool of air. And everything is still true. This still holds. This still holds. It's just now it's the density of air. And we're in a big ocean of air, aren't we? That's what my globe's for. The atmosphere is about 0.5% of the radius of the Earth, thick. So if this represents the Earth, and the radius, is half this, 0.5% of that distance is roughly about this. So there's the atmosphere to scale, roughly. A lot of people think that our atmosphere is really, really thick. Well, it is. It's like 30 kilometers up to where they claim space, But there it is. That's the whole thing. Not much, is it? However, there's enough there. To us, that's a whole lot of air on top of us. And so we have what we call atmospheric pressure. Does anybody know what the value is off the top of their head? Atmospheric pressure. What we're feeling right now, but we're just so used to it. I don't expect you to know, but no. 100 kilojoules. You're close. The unit's Pascal. Yeah, it's about 100,000, kilopascals. It's 101.3, kilopascals. Or something maybe more tangible that at least Americans maybe can understand. 14.7 pounds per square inch. So about 15 pounds on every square inch. I can imagine that. Now, that's at sea level, which is higher or lower than us? Lower. So would you expect the pressure there to be greater or lower? Greater. It's deeper. It's deeper in our ocean of air. So we're up higher. We're at what, 4,000 or 5,000 feet above, depending on where you live in the valley or the mountainside. That's a lot up. So that's a lot of air we don't have pushing on us. So here the pressure decreases to about 13 and a half pounds per square inch. So imagine a 13.5 pound quarter. That's roughly a square inch. Put that on your arm. Work with me. Imagine that. Yeah, you can feel that, but that's not too bad. Now take a second 13.5 pound quarter and put it right next to that one. Oh. Now cover your entire body with 13.5 pound quarters. That's what you're feeling right now. Yeah. So next time you're feeling wussy, remember that. You have a little pick-me-up. That's atmospheric pressure. So why don't we just implode? Because that's pushing on us right now. Because we've evolved to deal with it. There's truth to that, yes. There's a more physics, simpler explanation as well, though. We push back. We only notice air, really, the pressure, when there's a difference in pressure. And the pressure inside us and outside of us is the same. And so there's no difference in pressure. Remember like buoyant force? If it's greater pressure at the bottom than it is on the top, you feel a buoyant force? Because of the difference in pressure. By the way, we do too, right? The pressure is greater at my feet due to the air than it is at my head. Not much, but there is a slight difference, right? And that creates a buoyant force. Well, it better because I'm displacing air. Who wins though, my buoyant force or my weight? Yeah, I'm a lot heavier than the buoyant force I'm producing. But there is a buoyant force there helping hold me up. So, who would like to feel this? I got a demo for you. It's fun. I'm happy to. Any other takers? Give somebody a chance. Well, then you're up. Come on down. I'm going to ask you to get into this bag, face the audience, down on your knees. So, yeah, crawl on in there on your knees and pull it up around your neck. Pretty please. We won't go over the head, right? He needs to breathe. I got a shop vac, and I'm going to pull the air out from inside the bag. What's that going to do to the density of air inside the bag? I'm going to pull some air out of the bag. Yeah, it'll decrease because there'll be less matter, less air inside that volume. So you hold that inside. That's your job. Anywhere. You're comfortable. I got to seal you up here. You good?
Yep.
All right. Good enough. Well, let's pull some of the air out. All right, stand up. No, come on, seriously, stand up. Can you wave? We'll free him up. All right, thank you. Before you head back to your seat, though, I got a question.
Okay.
Did it hurt?
No, not at all.
What did it feel like?
Like someone was sucking all the air out of me.
Thank you. So we really only notice atmospheric pressure once there's a difference. And if we change our elevation fast enough, we note that difference because pressure is different with depth. Now, a shop vac might pull, I don't know. It might drop 13.5 pounds per square inch to, say, 11 pounds per square inch inside the bag. Difference of only a handful of pounds per square inch. However, no offense. Look. A small change in pressure, that wasn't that great. I didn't pull a lot of air out. But over a big area, lots of square inches, you get a big enough force that he couldn't stand up. It trapped him, essentially. So if you can spread pressure over a large area, that's Pascal's principle, you can get a big force. Here's another thing. Here's a silicone pad. It's not sticky. There's no adhesive or anything. You plop it on the stool, center it. Then I can lift the whole stool up. Why do they stay together? Yeah, there's no trick here. Think of suction cups or toilet plungers. What do they do when they get in contact with the surface? they push some of the air out from in between them, don't they? Well, how does the pressure compare in between the two objects compared to atmospheric pressure? It's less. So there's a difference in pressure. And the air in the room on top of this and underneath it hold it together. So it's the air in the room that's holding these together. If I let the air back in, then the pressure equalizes. There's no difference. If there's no difference in pressure over this area, there's no force to hold them together. Isn't that cool? Well, this is actually, recently they started these culinary aids. So the idea is you cook something, you got leftovers, or it's going to be a moment. Instead of having to whip out your saran wrap and cover it up to keep it fresh, well, look at this. And I got a couple of them for my glasses. You know, you drink a little bit of your drink and you want it not to go stale, you can put one of these on top, or it just keeps floaties from getting in there. But you let the air back. Well, I won't do that. I don't want to dent the bowl. But yeah, and it's just because when it goes on, it pushes a little air out, decreases the pressure inside, and the air in the room hold the two together because it's over a big area. If we made this even bigger, like the hovercraft, that was a big area, wasn't it? There was enough force to counter my weight. It held me up so I could slide along. Since you guys are real big on volunteering, I'll help with this one. Let's push these two suction cups together. Push out some of the air. Oh. Slippage. Push it. Okay, we'll stop there. All right. We can do it because the area is not as big, but it's tough, right? Thank you. You okay? Good. I was probably the one to worry. So next time you have to fix your clogged toilet, remember that I watch some people with a toilet plunger and they're just kind of in the water, just kind of. Doesn't do any good. You actually need to get the suction cup down at the bottom. Make contact with the toilet, seal it off, and then push out some of that air. Whoops. And then it lowers the pressure in that region, and so the greater pressure out can maybe push the clog out from where it's clogging. That was profound, but you know what I mean. This has a release valve. If you let the air back in, I can lift it up. But yeah, stick it down and you can climb on glass walls like Spider-Man, right? Let's look at this guy. This is a balloon that I put inside the bottle. It's open to atmosphere, but it also has a hole in the bottom. So atmospheric pressure is on both sides. So the balloon does nothing. There's no difference in pressure. Let me increase the pressure by blowing up the balloon. Of course, it opens. But as soon as I let go, the pressure is removed. What if I plug it? Let's plug the hole in the bottom here. Seal it off. Now the air in there, it's at atmospheric pressure. But when I try to blow the balloon up, what's going to happen? I can't do it. Why? What am I doing to the air inside? Yeah, I'm increasing the density. I'm pushing on it and trying to decrease its volume. When you push on something, the volume decreases. Increase the pressure, volume goes down. That's another law. It's called Boyle's Law in chapter 15. And those of you that remember your ideal gas law, it goes along with that. But it basically means this. Or you can just think of it as pressure times volume stays constant for the same temperature change. So if you increase the pressure by blowing on the balloon, I'm increasing the pressure in the region inside the glass. Then its volume goes down. It compresses. Something that I hope seems obvious to you, but it is a physics principle that we can apply to things. So, this, though. Let me free it up so I can blow air out of here. It can expand out. Now I've sealed it off after I blew it up. It's still open to the atmosphere on this side. What's going on now? Well, I blew air out of here, right? But the air was able to go out. Then I sealed it off. What do you think the balloon did that you probably couldn't notice much of? As soon as I sealed it off, before the balloon wants to go back, and it did a little bit, which lowered the pressure in here. Before I plugged this in, it was at atmospheric pressure, right? If I seal it off and the balloon starts to contract, whoosh, just a little, well, that drops the pressure in there, doesn't it? Well, I haven't done anything to the pressure out here, and so the air in the room is holding the balloon open. Because there's a difference in pressure between out here and in there. And when I let this air back in, well, now they're the same, and so the balloon's free to contract. I've used this at scout camps. Oh, this is kind of messy. Let's see. Come around here. So here's a bottle with a hole in it. Okay, the lid's on. When I let go of it, pull this out, what's going to happen? You saw this, right? Wrong. Look, there's a few drops. Why isn't it squirting out? Pressure. There must not, yeah. What's holding the water in? It must be the atmospheric pressure out of the air. See, some water comes out. If you look closely, there's a couple bubbles and it's dripping a little. Well, what happens when a little bit of water comes out to the airspace in here? Look, I can squeeze it. And now there's some air in here. But how do you think that pressure compares to this pressure? It's less. Yeah, I've created a partial vacuum in here because this is sealed. And so the lower pressure here, greater pressure here, that's what's holding the water in. So if you build a big enough one of these with lots of holes, you got yourself a camp shower, right? Let it heat up in the sun all day, and then the next morning, all you have to do is go underneath, open it, whoops, clean yourself off. You know, scrub, rinse, and then you want time to rinse again. There you go. Close it back off, and the air will hold it in. Cool, huh? Let's do another one. Oh, I'm right here. Let's do this one. So if you go scuba diving, as you go down, the pressure increases. We got that, right? But you have to consider both now. At the surface, you have atmospheric pressure pushing on you. As you go under the water, you have the pressure due to the water on you, in addition to atmospheric pressure on top of you. You follow me? So you got air on you and water on you. And so as you go deeper and deeper, it compresses the balloon. This is a vacuum pump. So you're down there swimming, and you've had a lot of pressure on you, and it's actually pushed a lot of gas into your bloodstream. And this is what happens to you if you come back up too quickly. The pressure is going to reduce on you, correct? And the air in that balloon's at atmospheric pressure right now. But so is the air outside it. The balloon's sealed. It's going to stay at atmospheric pressure. The gas in you is at some pressure. If you lower the pressure surrounding the balloon, this is what happens. And all that can, if it comes out of your blood too quickly, an air bubble or gas bubble can go to your brain and kill you. So you got to rise up slowly. You can't. Scuba divers aren't supposed to come up fast. Or weather balloons. This is what happens to a weather balloon when it goes up into the atmosphere, right? Because there's less and less pressure up there, isn't there? So it expands. We'll talk more about that next time. Do you got any questions? Because we're done. Yeah, Ron?
mentioned that if there were no gravity,
Yeah, what's holding the air next to the Earth? Gravity. You get rid of gravity, and the air's jiggling around, it would jostle itself away. Yeah. And then we couldn't breathe, and we'd die.
So the air is
Yeah, it's made up of stuff. That's why we get this pressure, because it has mass. Yeah.